Welcome back, everyone. Today we are exploring one of science's greatest mysteries. We will be going over the forces of nature and what string theory is. So let's jump right into this video and learn more about the unseen, the untold, and the mystical reality we live in. Okay, so first off, we have to go over the forces of nature. The first one we will cover is gravity. Gravity is defined as the force of attraction on a body towards any other physical body containing mass. A key concept to this is that the more massive the objects in general, the greater the gravitational force applied. That's why the Earth keeps us on its surface, but why we are not pulled towards everyone and everything around us. The force is still applied, but it's not strong enough for us to feel and react to. The next force we'll cover is magnetism, which is defined as a physical phenomenon created by the movement of electrical charges, resulting in attractive and repulsive forces between objects. Fun fact, the Earth's magnetic field protects us from solar winds and solar flares that otherwise would strip Earth of its atmosphere, leaking radiation directly down on us. So, there are two more forces, both dealing with atoms. They are called weak nuclear force and strong nuclear force. Strong nuclear force refers to the force keeping the protons and neutrons in the nucleus together. Weak nuclear force deals with radioactive decay and how protons can be converted into neutrons and other subatomic particles. But now comes the hard part. It's an ongoing battle to try and connect these forces under a singular general theory. This comes into play when discussing one thing that has puzzled us forever: black holes. A black hole is a region of space-time exhibiting such strong gravitational effects that nothing, not even particles and electromagnetic radiation such as light, can escape from inside it. How about one level deeper? Black holes themselves do not have a size. That's right, zero volume. How can that be? Well, the gravitational pull is so intense on the body of mass that it is made of, such as a collapsing star or the like, that the matter is compressed infinitely small. You would think that there's a certain point at which the matter can't be compressed any further, but with a pull with as great a magnitude as this, it actually goes beyond the quote-unquote limit. Some laws of normal spacetime are contradicted. Density is an object's mass divided by its volume. Thus, with a volume of 0, the object is infinitely dense, without needing infinite mass. The quantities used to measure gravitational field strength are the scalar invariant curvatures of spacetime, which includes a measure of the density of matter. So an infinitely dense object has a huge gravitational pull. I give you black holes. Now, mainly we recognize black holes as being collapsing stars. However, some scientists hypothesize that subatomic particles themselves can be miniature stabilized black holes. I won't get into that because it opens up way too many doors for one video. So why don't we segue into string theory? String theory is a way of trying to generalize and rationalize a way for how everything, big and small, in the universe behaves. There are a handful of different branches within string theory, each trying a different way to explain how the forces of nature and matter within the universe can all be linked. In general, it works on a premise that everything that makes up the universe is made up of strings. Imagine a string as, well, a string, like thread. These strings can come in the form of loops called closed strings, or segments of a loop called open strings. And they are one-dimensional but require more dimensions to quantify their existence. Many subsets of string theory revolve around 10 dimensions, while others revolve around 11, and there are a couple that take more. What makes a particle different from any other, then, is the way the string vibrates. Each string has a certain vibrational pattern, or frequency, that determines what the behavior and properties of the particle will be. String theory also helps give rise to the graviton, a theoretical subatomic quantum particle that carries gravity. But yeah, imagine the vibrational patterns almost as the DNA of the particle. The string's vibrational pattern, much like the arrangement of the nitrogenous bases, is almost like the GPS of the particle. And the vibrations themselves are dictated by energy, leaving each string with a specific resonance. This resonant frequency gives rise to the many different particles in our universe. However, nothing is certain. This is a continuing battle between the theoretical physicists and the mysteries of the universe. The hope, though we have a lot left to discover, is that someday we will have a solid, proven equation and explanation for how everything, astronomically and quantum mechanically, behaves in the universe. Alright, well, that is all I have time for today, so thank you all for watching. If you enjoyed, let me know. You can catch me on Twitter and all that too, of course. Alright, thanks guys. Hope to see you all next time. Bye-bye.